In the present problem of gravitation, we have to find the gravitational force due to a hollowed sphere on a small sphere of mass small m kept outside the hollowed sphere. Now you can see the figure. We have a hollowed sphere. What is a hollowed sphere? Suppose initially we have some solid sphere from which some material has been scooped out, some material has been removed. So what will be the resulting object? It will be a hollowed sphere. So we have a hollowed sphere like this of radius r, in which you can see there is a hollow region of radius r by 2. And there is a small sphere of mass small m which is kept outside. It is given that the distance of the mass small m from the center C1 of the bigger sphere or solid sphere is d. And you have to find what will be the gravitational force exerted by this object, hollowed sphere, on this particle or small sphere. Now say what will be the key points which we have learned in gravitation which will be applicable. We have seen in gravitation that when the object is spherically symmetric, then for finding the gravitational force for any outside point, the whole spherically symmetric object can be treated like a particle at the geometric center. If we have a solid homogeneous sphere, then a solid homogeneous sphere is always spherically symmetric. But if we have a hollowed sphere, which is homogeneous, of course, why it is homogeneous? Because the density is same at each point of the sphere. And if the density is same at each point of the object, it will be homogeneous. But it is not spherically symmetric, because we have seen in spherically symmetric object, on any radial distance, the density will remain the same. It may change from one radial distance to another radial distance, but for each radial distance, the density will remain the same. In this case, you can see if you're moving on any given radial distance, say like this, the orange spherical surface, so the density is not same. Here, the density is non-zero because the mass is present, while in the hollowed region, the density will be 0. So on the same radial distance, the density is not same, so the object will not be spherically symmetric. And since the object will not be spherically symmetric, for finding the gravitational force for any outside point, the object cannot be treated like a particle at the geometric center. Okay. So what we will apply here, we will apply here the principle of superposition. We will make use of the property of a spherically symmetric object, or you can say solid homogeneous object, because as I told you, whenever you are dealing with a solid homogeneous sphere, it is always spherically symmetric. So finding the gravitational force for any particle which is located outside the solid homogeneous sphere, the solid homogeneous sphere is always treated as a particle at its geometric center. So we are going to make use of that property. So what we will do, we will have a solid sphere, say object A, and then we will have again solid sphere, object B. When we will have a solid sphere, object A, we will take the radius to be what? R. Okay. And then we will take a smaller solid sphere of radius how much? R by 2. Okay. And we can easily find the gravitational force because of the objects A and B, because A and B are solid homogeneous spheres which can be treated like particles at their geometric centers. Once you find the force because of A and because of B, it will be very straightforward to find the force because of C, because you can see the force due to C will simply, by superposition principle, the force of A minus the force of B. You can see if you remove the effect of B from A, you will get what? You will get the scenario of object C. So basically, we are, for the time being, we'll forget object C and we'll focus on solid homogeneous spheres, once object A and once object B. So let's see case 1. Suppose I am having a solid sphere, homogeneous solid sphere of radius r and mass m. It is given in the problem that the solid sphere, before the hollow was made, before the cavity was made, the solid sphere was having a mass m. So I'm taking the solid sphere mass as m, radius r, center C1, and I'm giving it a name object A, and there is a particle or a small sphere outside at a distance of d from C1. Now this whole solid sphere can be treated like a particle for finding the gravitational force. Since it is a solid homogeneous sphere, so it will be spherically symmetric as well. So it can be treated like a particle. So I'm replacing it with a particle model. See, in place of the sphere, I made capital M at the geometric center C1, and there is a small sphere of mass m. Now we have two particles. Say this solid sphere is exerting a force F1, gravitational force F1 on small m. So you can apply the law of gravitation and you can find F1. So F1 will come to be what? G capital M small m by d square. Okay, this will be your F1. So this is the force due to the solid sphere of radius r. Now consider object B, which is again a solid sphere, but now I'm taking its radius to be what? R by 2 and center at C2. So you can convince yourself. If you fill this small sphere in the cavity, if you fill object B in object C, say this is your object C. So if you fill object B in object C, you will get what? Object A. So all the material will have the same density. They will not differ in the density, okay? Because they are, I'm assuming the same material. So they will have the same density. So this is your object B. The center is C2, the radius is R by 2, and say the mass is M prime. Of course, M prime will be some fraction of M because it is a part of that bigger sphere. And the distance of small m from C1 was D. So what will be the distance of small m from C2? So can we say it will be d minus r by 2? Yes or no? It will be d minus r by 2. Now again you have a solid homogeneous sphere which can be treated like a particle at its geometric center. So I can replace the sphere with a particle m prime at a point C2. And this is your small m. So it will be attracting it with a force say F2, and the distance between the particles will be d minus r by 2. So by law of gravitation, F2 will be g m prime m by d minus r by 2 square. Okay. Now can we get m prime in terms of m? Because as I told you, all the objects A, B, and C have the same density. Then only you know when you will fill it, you will get the object C. So they must have the same density. So I need to get m prime in terms of capital M. So since density is same and we know mass is what? Density into volume, and since density is same, so you can always have m1 by m2 is what? Rho is same. So masses will be in the same ratio as the ratio of the volume. So you can say mass of A divided by mass of B is the volume of A divided by the volume of B. And the mass of A was M. Mass of B, we have taken M prime. The volume of A is a solid sphere of radius R. So it will be 4 by 3 pi R cube. And the mass of B, so B is a solid sphere of radius R by 2. So you will cancel out the common factor, and m by m prime will come to be r cube by r cube 8. So therefore m prime will be what? M by 8. So you can see the mass of that small sphere is coming to be 1 by 8 times of the whole solid sphere, bigger one. So if you are placing, just put this value of m prime in equation number 2. So F2 will be G. What is m prime? M by 8 small m d minus r by 2 square. Let it be equation number 2. Okay. Now what is left is simply the application of superposition principle. You got the force due to the solid sphere object A of mass m radius r, which is F1. You got the force due to a smaller sphere of mass m prime, radius r2, center C2, which is F2, this much. Now we have to find the force due to this object. So can we say by the superposition principle, simply you can say this force will be what? F1 minus F2. That will be the superposition, because if you see, if you want to know how much force this hollowed sphere will exert, simply find the force due to the whole sphere then subtract the force because of this smaller portion, which can be filled in the cavity. So you will get the force due to object C. So it will be F1 minus F2. And now since we have a 1D case, F1 is left side, F2 is also left side, so you can remove the vector sign and simply write F1 minus F2. So F will come to be G m small m by d square minus G. F2 was 8d minus r by 2 square. So what will be the final answer? We'll get F to be, we can take G m small m by d square common, 1 minus, you can also say 1 divided by 8. Now if you're taking d square common, it will be what? 1 minus r by 2d square. This will be your final answer. This will be the force on the small mass m because of the hollowed sphere. Okay.